So now we will go to the other pole through our second speaker, Dr. Arnold Gordon. So he's a professor from the Department of Earth and Environmental University and at Lamont Doherty Earth Observatory. He's a field-going physical oceanographer whose research is directed at the ocean's stratification, circulation and mixing, and its role in the Earth's climate system. So today, Professor Gordon will give us a talk entitled The On and Off Again Weddell Polynya. Let's all welcome Professor Gordon. Professor Gordon, please take it away.
Unmute. I might even show my picture. Okay, let me put it on play. I assume you can see this. Okay. So the big schematic there is from an article in Scientific American in 1988 that I wrote with Joey on polynyas of the Southern Ocean. And as Claire has shown, is great extent of sea ice around Antarctica in the wintertime.
Excuse me, Professor Gordon.
Yes.
Can you please switch the slide because we're looking at the handout slides. Yeah.
Yeah. Okay. I wonder how I do that then. Never had that problem before. I used to all the time. Don't quite know how to do that. Maybe what I'll do is stop sharing. Oh, come on. So maybe what I'll do is stop sharing. I'll put the PowerPoint on the other screen and see what happens. I don't understand why that went on that way. Give it another try. All right, share screen. Not there anymore. All right, so let me go to PowerPoint and open it. Sorry about this. Doom. And where is it? Close that. Share screen. Ugh. Sorry about that. Let me see what happens now. I don't know. I'll put it on play.
Perfect.
What's that?
It's perfect now.
Wow, isn't that
okay,
odd?
Great.
Okay, big schematic there of the article I had Scientific American with Joey is you have extensive sea ice cover in Antarctica in the wintertime, but there are some holes in the ice in the winter. There's the coastal polynyas, which are what we call latent heat polynyas. This cold wind off Antarctica blows the ice away as fast as it forms. And heat flux to the atmosphere is driven by the latent heat of fusion. However, in the open ocean, there occasionally is a large area of open ice in the winter, primarily in the Weddell Sea. And I'll talk about first the Antarctic sea ice cover and then the Weddell. But first I'd say is that thanks, Joey, for greatly increasing my H-index. With 9 highly cited co-authored papers, and that's the list of the papers. Some of them are well over 100, which is fantastic. So thanks again, Joey. Let me get into it. So, okay, so Claire mentioned that the Arctic ice, of course, is decreasing quite rapidly. And the Antarctic ice actually has been sort of kind of steady. In fact, one could even think it might be increasing a little bit. Though in recent years, in about 2014, there's been a sudden decrease in the ice that a lot of people are curious about and trying to understand. So let me say something about the sea ice cover, and then I'll get to the Weddell Polynya. So in order to understand this Antarctic sea ice, you have to understand the ocean below. It's because the air above is quite cold, well below freezing. So what actually melts the ice, a big part of that is ocean heat. So here's a meridional ocean circulation in the sea ice zone and the Antarctic margins. Let me see if my arrows, yeah. So you have this warm deep water coming in from the circumpolar deep water coming in from the lower latitudes, and its temperature is about 1 degree Celsius, almost 2 degrees, 3 degrees warmer than the freezing point. And that water, some of it mixes up into the cold surface layer, which in wintertime is covered by sea ice. Some of it spreads onto the continental margins of Antarctica to supply the heat there, which interacts with the glacial ice. The coastal polynya plays a role there in controlling the stratification. I won't talk too much about the continental margins. I want to talk more about the open ocean. So to bring the heat up from this 1 degree water into the freezing water in wintertime, there's a picnic line that separates these two layers, and it's really rather weak. There's the cold, low salinity water on top, warm, higher salinity water below, but their densities do not differ that much. It's weakly stable, so there's stable but only weakly stable. So there's a lot of vertical mixing that can bring that warm water up to the top that can influence the ice. Now, what can let's see now. So the idea there is, when you always can blame some climate index for something or other, and here we'll focus on the southern annular mode, SAM. And during the positive SAM, there's increased precipitation. There's Antarctica. There's the sea surface there, and the sea ice zone over there, and this warm deep water is below it. So during the positive SAM, the cold dry air from Antarctica does not spread over the ocean as much as it does during the negative SAM, which is here. The maximum westerlies tend to be a bit further south during the positive SAMs than they are during the negative SAMs. So during the positive SAM, it's not as cold, but more importantly, there's more storms and precipitation over the sea ice region than there is in the negative SAMs, when the cold dry air prohibits the invasion of the moisture airs from the circumpolar belt. So in addition, just the glacial ice is important. In addition, there's increased glacial ice melting around the margins of Antarctica, and that injects fresh water into the surface layer and picnic line layer. That also has an inhibiting effect on the upward movement of the warm deep water. So in a positive SAMs, surface layer within the seasonal sea ice zone is made fresher due to excess precipitation over evaporation, leading to a more stable surface layer, less heat going up. Negative SAMs is the opposite. Surface layer gets saltier, making the sea ice zone more susceptible to vertical exchange processes. And also, as I'll say later, leads to the possibility of open ocean convection associated with the Weddell Polynya. Much of this is published in this paper, which Joey was the co-author in 2007. And here's just, for instance, the SAMs in this region here in the Weddell, in the Weddell region. There's the latitude and longitude. So that's SAMs from 1980 or something like that. And, it's becoming more positive. It goes up and down, positive and negative, but generally becoming more positive. And the trends in precipitation over the Weddell have also becoming higher, as consistent with the more positive SAMs. The next hidden slide, it deals with ENSO. ENSO, El Nino, La Nina, also plays a role, surprisingly, in the sea ice distribution in the Weddell area, but I won't get into that now. SAMs is the more important one. So just to summarize, I think what's going on now in the sea ice and why it's not decreasing as it is in the Arctic is it's generally colder than freezing in the surface layer, and you have more as SAMS becomes more positive. You're getting a more stable pycnocline, more stable separation of the cold water with the warmer deep water, less heat coming up, less melting of the ice with the deep ocean heat. So I think the ice is, I think that actually is probably an important aspect of why the sea ice is not decreasing, the positive. And also there might more glacial melt is spreading through the pycnocline also, and that may be another factor to stabilize the upper layer. But now that strange Weddell Polynya from 1974 to 76, and it's really this that got me involved with the NASA group and the microwave satellite data. And so there's discovery when the microwave satellite was turned on, and I said 1973, but when Claire said 1972 perhaps. And all of a sudden, there was, in the winter of 74, 5, and 6, this open ocean area near the Greenwich Meridian. All that color, that's all ice, and that's open ocean right over there. Surprise. So what a coincidence. You turn on a satellite so you can look at the sea ice and you see there's a big hole of Polynya in the sea ice. Oh, so therefore it must be there all the time. And that's wrong. Not there all the time. The Great Weddell Polynya of the mid-70s, big ice-free area, about 250,000 square kilometers, drifting westward, if you notice, at about 1.3 centimeters a second, with the general circulation of the Weddell Gyre. The Weddell Gyre is a clockwise gyre, and this water is flowing towards the western boundary. And it's in order to maintain this open area in the wintertime, you need a lot of heat convected up to the surface layer from that deep water. And it was fortunate. I was working in this area in January, February 1977. So the austral summer following the Polynya in the winter of 76. And we found a strange thing. Now, so there's the temperature, for instance, that we measured. This is the pre-Polynya temperature as measured in 1973. Forget which ship measured that. This is in this paper, the Gordon 1978 paper. And what we measured in 1977, after the Polynya, much cold water down to about 2,800 meters, also fresher. So this heat, missing heat, was most likely the heat that kept that sensible heat Polynya going, with convection therefore down to almost 3,000 meters. The convection, how much water had to convect? Well, if this water coming down was freezing, you needed a certain amount of freezing level, -2, -1.9 water, to account for that decrease in temperature down to about 3,000 meters. And we think there was about 1.6 to 3.2 spherodrops, million cubic meters per second, averaged over the 3 years of freezing water is required to account for that cooling down to almost 3,000 meters. Amazing. We explained, and I must say, interesting, that when I was down there on this, it was an Argentine ship, measuring this, I did not know about the Weddell Polynya, because I didn't know about that data yet. And it's only at some point directly thereafter when I saw Carsey's paper on this that I realized, boom, these are connected. That's why we had the Weddell Polynya. Okay, so just to bring back to the SAMs, positive SAMs. In the positive SAMs, stronger pycnocline, more fresh water going into the surface layer, stabilizing it, maybe more glacial ice melt coming in there too. Decreased the mixing upward of the warm deep water, the sea ice was extensive. During the negative SAMs, you make the surface water saltier. maybe saltier enough so that its density equals the density of the water below, and boom, you get deep reaching convection and the Weddell Polynya. That was the explanation that we provided in, I forget which, paper I did in 1982, maybe 2007, but I summarize it in this 2014 paper in Nature Climate Change. Okay, now, so let's see now, let's look at SAM over the century and see what happened. It's becoming more positive in recent years. This was the Weddell Polynya in the mid-70s, and it was a long period of negative SAMs beforehand. That's consistent with the story that I presented, that the negative SAMs led to more heat coming up to produce the Weddell Polynya. But it's been negative in other times before. I will go back to this one in the first decade of the 20th century. This was measurements then made by the Deutschland in 1912. I always found it was interesting here. Oh, I didn't put this information on this. Okay, no, here it is. In the first part of the first decade of the 20th century, the Deutschland expedition in Weddell found a record of no stratification. They did not find the warm deep water at about a few hundred meters down. And Georg Wüst, in 1928, interpreted the Deutschland data as convection. He identified that there was deep convection of the warm water up to the surface based on the Deutschland data. And there was no mention of a Polynya or anything. Nobody knew anything about that. But the idea was there was deep convection in the central part of the Weddell Sea, as shown by the Deutschland data. In later observations in the 1920s, they did not see that. They did not see the warm deep water was there with a stratified pycnocline, and that explanation of the Deutschland data kind of disappeared. There was a negative in the late teens, but no data. There was another negative, extensive negative in the 1950s, and there's two or three data from an Argentine ship in 1958 that indicate there might be deep reaching convection. But the Argentine data at that time had a lot of problems with salinity, and it'd be hard to make that story. So here, when we turned on the microwave, we saw this deep reaching convection going on, and there was a big negative SAMs in the previous years and deep convection, and maybe there was deep convection in the first decade of the 20th century. Okay, now, what about the glacial times? It's interesting. Sea level, 130 meters lower. Glacial ice, much more extensive around Antarctica. I think there was, what I call it, was a very serious negative SAMs. And I think during the glacial times, the Polynya mode of convection was the common mode of convection around the Southern Ocean. And why is that important? Is because the water that comes up is there for only a day or two before it can sink. Not enough time to exchange its carbon dioxide with the atmosphere. So when you have an open ocean convection, as I think was the common thing in the glacial period, the ocean did not get rid of its CO2 into the atmosphere, and you were able to build enormous amounts of carbon dioxide in the deep ocean. Okay, almost finished. So I think that during the glacial periods, the Weddell Polynya was the common way of ventilating the deep ocean rather than the continental margins. What about the future? The SAMs is becoming more and more negative in the recent decades. This solid line here is, it's in there someplace. The smooth black line shows decadal variations of SAMs, obviously becoming more and more positive. Surface layer is going to become more and more stable, less possibility of Weddell Polynya. Eventually, the sea ice will stop growing. it's or staying the same because the air temperatures are going to go spend a lot of time above freezing, and perhaps the ice will start melting just because for the reasons in the Arctic, warm air rather than heat coming up from the bottom. Strange thing is, and this I think is my next to last slide, here in 2017, all of a sudden there was this more rise Polynya, this right over there. There's a little topographic feature right there that induces upwelling, and we had a very common occurrence of the more rise Polynya during 2016 and 17. And here's a figure that was in our paper in 2007 that Joey then updated up to 2018. And this shows the amount of days, number of days, that you had a Polynya over Maud Rise. There's Maud Rise right over here. There's the warm deep water. You have a GI Taylor column over Maud Rise and a good setup for convection. And what happened in 2016 and 17, a much more common occurrence of the Maud Rise Polynya than in the previous decades. There were peaks here and there. What happened here? And what happened here, this was a paper I did this year in something, geophysical newsletters. There was an extraordinary spin up of the wind curl over the Weddell Sea, spinning up the gyre that lifted up the pycnocline over Maud Rise close to the surface. And that induced more upwelling around Maud Rise. However, Maud Rise Polynya does not ensure the sparking of a Weddell Polynya. And that's because if we spin up the gyre, which happens in a positive SAMS, it doesn't necessarily mean that the entire region can start deep reaching convection because the surface water is low in salinity. This is more of a dynamic kind of uplifting of the pycnocline rather than a thermodynamic instability. So I think we're going to see more Maud Rise Polynyas as SAMS becomes more positive, but that not necessarily spark a Weddell Polynya because the surface layer is too low in salinity. So my concluding remarks, the sea ice is changing, and we need you to document it and tell us why. And happy birthday, but keep on working. That's it, thanks.
Thanks, Arnold.
Yeah, let me stop sharing so that you could. Okay, go ahead.
Thank you so much, Professor Gordon. That's a really interesting talk.